Each of these uranium fuel bundles produces enough heat to generate 1 million kilowatt-hours of electricity. But how is enriched uranium obtained? We visited the world's largest high-quality uranium deposit and a nuclear fuel factory to discover how uranium is extracted from nature and how one of Earth's most dangerous metals is processed. Uranium is a metallic element discovered by a German chemist in 1789. The significance of this discovery wasn't understood until a century and a half later, in 1938, when scientists discovered that uranium atoms could be split to produce energy. To obtain uranium, they dig approximately 1,700 feet underground at a site in northern Saskatchewan, a province in Western Canada, known for hosting some of the world's largest and richest uranium deposits. The extracted uranium is primarily used as fuel in nuclear reactors to generate electricity. This mine is the largest source of high-quality uranium in the world. The uranium ore lies beneath a layer of water-saturated sandstone. To reach it, they use tungsten carbide drills. Like knuckles in a fist, the drills penetrate the rock face. These initial holes are for tubes that will extract heat from the ground and freeze it around the ore. The miner operates the equipment remotely, transferring a new piece of tubing to the end of the drill every feet and a half. To penetrate approximately 430 feet into the sandstone layer, it takes up to 8 days to install just one length of tubing, and there are 200 of them. They set up the tubes to surround the mineral deposit. These freezing tubes stabilize the ground and also turn the high-pressure groundwater into ice, so it doesn't interfere with mining. An above-ground freezing plant cools the calcium chloride brine to minus 22 degrees Fahrenheit and distributes it through the freezing tubes. The brine absorbs heat as it freezes the ground and recools above the uranium deposits. Now they're ready to extract the ore. They'll use a drill to bore into the mineral body and make an initial hole of small diameter, known as a pilot hole. The pilot hole traces the drill's path to the mineral and creates an entry point for larger mining equipment. From an elevated position, the drill bores vertically into the rock to reach a specific level below the mineral body. Now they're ready for the expansion bit. The drill lifts the expansion bit through the pilot hole, widening it. A remotely operated wagon picks up the rock. This remote control system keeps miners safely away from falling rock hazards and also minimizes their exposure to radioactive uranium in the mineral. As an additional precaution, they continuously ventilate the mine by introducing fresh air every 20 minutes. Guided by the operator's control lever, the wagon delivers the ore to a scanner. By measuring the amount of radioactivity in the ore, the scanner determines that the uranium content is approximately 15%. In much of the ore, the uranium content is even higher, averaging around 18%, and that's considered very high quality. The wagon now empties the ore into a chute. From a control room, an operator manipulates a hydraulic hammer to crush the ore into pieces. The crushed ore is fed to a mill that grinds it into a fine sand. They then add water and it turns into a slurry that is pumped to the surface. Trucks transport the uranium slurry to 50 miles away. They stop at a special offloading facility. The vacuum system stand aligns with the container enclosing the uranium tank. Once in position, a vacuum tube drops into the tank and suctions the slurry. After a wash and irradiation check, the truck leaves the facility. The ore in powder form is treated with acid to obtain the uranium. The uranium mixture is introduced into large acid-filled tanks. The acid dissolves the uranium, but not the rest of the rock. The rock settles to the bottom of these tanks. The uranium acid solution flows forward, leaving unwanted minerals behind. Using a series of chemical reactions, they further purify the uranium. Then, they heat it to 1,532 degrees Fahrenheit. First, they convert the uranium into gas to enrich uranium-235, which is the isotope needed for chain reaction. This gas is fed into centrifuges, where centrifugal forces are used to separate uranium isotopes based on their mass. Uranium-235, being slightly lighter than uranium-238, concentrates more in the center of the centrifuge, allowing for its separation. Once separated, it's concentrated into a coal-like black powder. The uranium powder flows into 210-liter steel drums. The drums are then sent to a nuclear fuel processing plant. The uranium changes from black to yellow as they convert it into uranium trioxide, an intermediate chemical form in the processing chain. They send the uranium trioxide in specially designed inverted cones. Upon arrival at the facility, a valve opens at the bottom, and the powder flows into conveyor tubes that carry it to the plant. Inside, they dissolve the uranium trioxide powder in acid. A worker takes a sample to test density and chemistry and confirms both are acceptable. They then add a chemical to convert the dissolved uranium into solid. After further processing, the uranium trioxide becomes uranium dioxide, the chemical form required for nuclear fuel. By centrifuging the uranium dioxide, they mix particles of different sizes to make a more homogeneous blend. Chemical processing has also changed the uranium's color. Now it's a fine black powder. Using several tons of pressure, presses mold the uranium dioxide into pellets. A rotating wheel with protrusions guides the pellets onto a channel conveyor. A uranium pellet the size of a peanut generates the same energy as 800 kilograms of coal or 560 of oil. The conveyor carries the pellets to an oven for 24 hours. The heat removes the pellet's pores, which contract, increasing the uranium density. A robotic arm loads the pellets onto a tray and levels them. The conveyor moves the tray forward, and a robot places zirconium fuel tubes on a rack. Zirconium is a metal highly resistant to both heat and corrosion, but neutrons will pass freely through it during the fission reaction. The tube rack meets the incoming pellet tray. A robotic loader pushes the stack of 30 pellets into the tube. The pellets are placed inside metal tubes, which are then joined into fuel assembly elements that go into the reactor core. The tubes pass one by one to an automated welder that seals the ends. The next robot retrieves the complete uranium fuel rod and transfers it to an assembly device. After the rods have been welded and the package capped at both ends, a robot transfers it to a scale. This scale confirms the correct amount of uranium in the package. Before burning in a reactor, the amount of radioactivity emitted by the nuclear fuel bundles is very low, and they're safe to handle while workers prepare them for shipping. This nuclear fuel is packed with enough uranium to power 100 homes for a year. The fuel is received at the nuclear plant, where it will be inserted into the reactor core. In nuclear reactors, uranium serves as the trigger and acts as the initial energy source for what ultimately becomes electricity. Each of these uranium fuel bundles produces enough heat to generate 1 million kilowatt-hours of electricity. To bring them to life, they must be inserted into the reactor core. The 480 reactor tubes can each contain up to a dozen fuel rods, and when 5,760 rods are in place, the show begins. Nuclear fission converts matter into energy released as huge amounts of heat. Some of the uranium atoms inside these fuel rods are excitable, and when excited, they begin to release neutrons in all directions. The tiny neutrons can pass through the zirconium walls of the fuel bundles, flying from one tube to another until they collide with another uranium atom. When they do, the atom splits, releasing energy and more neutrons, and thus a nuclear chain reaction is obtained. But when it accelerates too much, it needs to be stopped. If not, what scientists call a nuclear reactor malfunction occurs. The reactor is not only sealed between 7 feet thick reinforced concrete walls, but it also shuts down automatically if the temperature rises or the pressure drops too fast. The heat is used to turn water into steam, a process carefully controlled from the control room of the plant. The enormous turbines placed in 1,300 feet long and 20-story high rooms convert steam into electricity. The turbine spins at 1,800 revolutions per minute and powers a generator. The gigantic generator wheel converts the motion into over 750 megawatts of electricity, enough to meet the needs of 500,000 people. After approximately a year in the core, the fuel bundles are spent, but they're also extremely hot and radioactive. They're so hot that the rods must be stored in water for 10 years before they can be safely disposed of. They're placed in a pool at the plant to lower their temperature and dissipate radioactivity. Sunken in the depths of this 25 feet deep pool are over 700,000 radioactive fuel rods. If you enjoyed the video, you can watch similar videos clicking them on screen. Also, subscribe to this channel by enabling notifications to keep learning.